Hello everyone, today we are going to discuss course schedule. This is a classic case of topological sort, and that is the video that I made yesterday. So if you want to know a bit about topological sort, I'll suggest you guys to go through the video. But let's start with this question, with this problem. Here, what is the requirement is, let's suppose there are 2 courses, 3 courses, 4 courses, any number of courses can be possible, and we are given a 2D prerequisite array where each set will tell you which from which course to which course you can go. Basically, if you want to do course 0, you have to go through 1. 1 is a prerequisite to do 0, and same is that 0 is the prerequisite to do 1. To explain it in a better way, I'll take a better example, because I think 0101, just 2 courses, might not be enough to get a proper understanding of the problem. So let's suppose the number of courses that we have is, let's suppose, 4. Here it is saying that 0 to do 1, we have to complete the course 0. So 0 and 1 can be a pair. We can say that, okay, maybe our prerequisite have this pair, and we are saying to do course 3. Okay, so to do course 2, 3 needs to be completed first, and to do course 3, 0 needs to be done before 3. Okay, so if I have to represent this, we can say that, okay, we know that, okay, for 1, 0 is compulsory, for 3, 0 is compulsory. In this direction I can put this, and for 3, 2 is compulsory. So I can see there is no cycle, there is no internal dependency, that maybe this 3 is then pointing to, let's suppose, let's suppose it might say that to complete course 0, 2 is a prerequisite. So this is not possible. At the end of the day, to do course 2, you have to do course 3, and to do course 3, you have to do course 0. But now if there is one more prerequisite array that is given to us, that is to do 0, we have to do 2. So we can see there is a cyclic dependency, right? In those cases, we can say that no, we will not be able to cover all the courses in line, because anyway there is a deadlock. One course is dependent on other course, and the other course is also dependent on some other course, and at the end of the day there is a deadlock. So basically that's what we have to tell in the solution as well, that if you are able to complete all the courses, then return true. If you are able to finish all the courses, then return true, else return false. This is what they're expecting. So as I mentioned, it's a classic topological sort. That's where it comes in the picture, that there is, what topological sort tells us, that there is a node u which denotes u, and v which denotes that before reaching v, we have to reach till u. That's kind of similar thing or similar pattern we can see here as well. So what we are going to do, we are going to map down all these connection in form of a adjacency graph, and once that is done, what we can do, we can pick up all those nodes which have no dependency, and add it inside my queue. So at least we are sure that to complete these 2 nodes, or these 1 nodes, or these x nodes, we do not require any other prerequisite. So we know these nodes are safe nodes, we can pick these nodes. And how will I know that whether these nodes are safe nodes or not? That's where the in degree concept comes in. Okay, so let me draw this better so that things are a bit clearer. So let's suppose there is a combination such as this, and let's suppose this. Okay, so here I can see maybe this is also there. Okay, here see, if you see this carefully, what it is saying, to complete course 1, you must do 0 and 4 first. That's the prerequisite to do course 1. So here I know that this one is dependent on two courses, and we can see this in the diagram as well, that there are two nodes, two integers that this node have. That's what integer is all about. Integers tell us that what all, how many nodes a particular node is dependent on. So if I have to draw a diagram, I'll show you. This have one integer, correct? This have 0 in degree, correct? Because it is not dependent on any other course. This is also 0 degree in degree. This have 2 in degree. This course is dependent on two courses. This have 1 in degree and this have 1 in degree, correct? That's the concept that we are using. We are checking all the nodes whose in degrees are 0. That means who are accessible or who do not have any prerequisite. We'll pick those nodes and add it to our queue, and then we will say that okay, I can pick up 0 because it is not dependent on any other node, fine. And now assume, in this while loop what we are doing, now assume this 0 node is not even there, because let's assume you have already done course 0. That means this dependency is no more there, correct? Correct. What we are seeing, this dependency is no more there. That means the count that we had initially was 2, but now it will get reduced to 1. Similarly for 4 also, it will say that yes, there is no dependency on me as well, I am backing out. That means my in degree count will further reduce to 2, and we are waiting for that moment that whatever course this 1 is dependent on, once these two are accessible, that means 1 is also accessible, because these two do not require any additional courses, or these are not stuck in a cyclic loop. That means 1 is also not stuck in a while loop. We can get done with course 0 and course 4, and then we can go to course 1. So that's what we are doing. We are picking up those degrees or those nodes which have 0 in degrees, and we are removing all the adjacent nodes to those degrees, and accordingly we are decreasing the in degree and checking if at any point for a particular node, if the in degree becomes 0, that means this course is also accessible, please add it inside your queue, and so on. And at the end we will see, are we able to reach to all the courses? Is the number of courses that we have reached till now, is it equal to the number of courses that we have to do? If yes, then yes, all the courses are accessible, else it is not. So this is the entire code and everything. So I'll quickly take a minute to explain you one more example. So let's take similar example, but the only difference it will be is that this 0 have a dependency on this 2. Okay, let's suppose something like this is there. So let's, if you see this carefully, let's suppose 4 is also there. Okay, so I first, what I'll do, I'll calculate the in degree for all the nodes. Okay, so for this node there is 1 in degree, for this node 2 in degrees are there, for this node 1 in degrees there, 1 in degrees there, and 0 in degrees there. Now as per code, we will pick up those nodes which have 0 in degree, which are not dependent on any other course, that is 4. Okay, I'll add this 4 inside my queue, fine. This is 4 that I just added, and then I'll check, is there any other value that I can add? No. Then the while loop starts. I'll remove this 4 and I'll ask whatever adjacent nodes that you have, please remove your dependency from there so that their in degree get reduced. So the in degree for this one will get reduced to 1, but still we can't add it inside my queue because this 1 is still dependent on the 0. Fine. Now we can see, although our queue is now empty, we are out of this while loop and our count is just 1 and not 4. So anyways, we can say that yes, there was some cyclic dependencies. We were not able to reach to 1 because 1 was dependent on 0 and 0 was not reachable because it was dependent on 2. So that's how in degree helps us to know that okay, this course is accessible, please remove all the dependency from this node. You have already done this course, now move on to the new course. But what if the new course is anyways dependent on some other course which you have not done till now, correct? And that course also depends on some other course which you haven't done till now, and you can't do anything about this, right? So that's the approach, fine. And let's quickly discuss about the time complexity. So what we are doing, we are going through all the prerequisites that we have and we are mapping them up. So for this particular portion, it will be number of prerequisite, that will be n, fine. then we are looping, we are adding uh, all the for okay. So what does this represent? This represent that we will be taking each node and we will be traversing through all the neighbor of that node, and it is a directed graph, right? So if there are four nodes, correct, and there will be let's suppose e edges, so we can say that the total number of time this queue will get processed will be the number of nodes that you have plus the number of edges that you have. And if we talk about number of edges, it's nothing but the number of prerequisites. So the time complexity for this particular section of the code will be number of courses plus the number of prerequisite array, the whatever the length of the prerequisite array, that plus the number of courses that we had. So this is the total number of time this queue loop will execute, or these many values will get added in my queue at the end of the day. Fine. And if we talk about the space complexity, then I can see that this will be O of number of courses, and the queue, in the worst case, we can assume that all the courses are independent, correct? In that case, all of them can get added to my queue. That means my queue can have, at max, on the worst case, can have the total number of values that my queue can hold will be equal to the number of courses that we have done, that is given to us. So the space complexity will be length of number of courses, basically. So this will be my space complexity, and we were discussing about the time complexity as well, that will be equal to the number of courses plus the edges, that is the length of prerequisite array. So this will be my time complexity and space complexity. All okay, hope this helped you, and that's all. I'll try to share this code in the comment section. Let me know if I can help you in any other way, and if there is any other question you would like me to pick up, please let me know. Thank you.